In 2011, a man named Daryl LaCourse was sitting at his home computer, scrolling through graphs of starlight. He was not an astronomer. He had no degree in physics. He was a volunteer, one of thousands of ordinary people who had signed up for a project called Planet Hunters. The idea was simple. NASA's Kepler space telescope had been staring at a patch of sky for years, recording the brightness of over 150,000 stars. When a planet crosses in front of its star, the brightness dips slightly, typically by about 1% for a Jupiter-sized world, less for smaller ones. Computers caught most of these dips, but some patterns were too irregular, too strange for algorithms to flag. So the data was put online, and volunteers were asked to look. LaCourse looked, and he found something that should not have been there. A star, catalog number KIC 8462852, was dimming. Not by 1%, not in a smooth repeating pattern. The brightness dropped by up to 22% in irregular asymmetric dips that lasted days. Then it came back. Then it happened again, differently. Nothing in the Kepler database looked like this. He flagged it. Other volunteers confirmed it. The data made its way to professional astronomers, and in September 2015, a team led by Tabitha Boyajian, then at Yale, later at Louisiana State University, published a paper with a title that became instantly famous in the field. Where's the Flux? The star was roughly 1,470 light-years from Earth in the constellation Cygnus. An ordinary F-type main-sequence star, slightly larger and hotter than the Sun, about 50% more massive, roughly 1,000 degrees warmer. By every standard metric, it should have been unremarkable. It was not. What Kepler saw. To understand why the data was so strange, you need to know what a normal transit looks like. When a planet passes in front of a star, the brightness dip is symmetric. It goes down, stays flat for a while, comes back up. The shape is predictable. The depth tells you the size of the planet. The timing tells you the orbital period. This is how Kepler discovered thousands of exoplanets, by catching these clean, repeating signals in the light curves of distant stars. KIC 8462852 did not produce clean signals. Over the 4 years Kepler observed it, from 2009 to 2013, the star showed at least 10 distinct dimming events. 2 of them were massive. One, around day 793 of the mission, saw the star's brightness drop by roughly 15%. Another cluster of dips, between days 1490 and 1580, was even more complex. Multiple overlapping dips, some sharp, some gradual, reaching a maximum depth of 22%. For comparison, if Jupiter crossed in front of the Sun as seen from a distant star, it would block about 1% of the Sun's light. Whatever was blocking 22% of KIC 8462852 had to be enormous, and it was not following any regular orbit. The dips were not periodic. They were not the same shape. Some lasted a day, some lasted a week. Some had sharp edges on one side and gradual slopes on the other. This ruled out a simple planetary transit. It also ruled out an eclipsing binary star, and it ruled out most known forms of stellar variability. KIC 8462852 was a mature, middle-aged star, not a young object surrounded by a protoplanetary disk. The team considered and rejected numerous possibilities in their paper. Instrumental error was ruled out early. The signal was too strong and too consistent across multiple analyses. A background eclipsing binary was ruled out through high-resolution imaging. The star showed no excess infrared emission, which meant there was no large, warm dust disk around it. What remained was a puzzle, the hypotheses. Let's go through them. The first serious proposal from Boyajian's team was a family of comets. In this scenario, a large comet or group of comets had been disrupted, possibly by a gravitational interaction with a nearby body, and the resulting debris cloud was passing in front of the star. Comets can produce irregular, asymmetric transit signals because they are not solid spheres, but loose collections of ice and dust, often trailing long tails. A shattered comet family could, in theory, produce the kind of messy light curve Kepler observed. The problem? Scale. To block that much starlight, you need a staggering amount of material. The comets would have to be not just numerous, but enormous, and precisely arranged to transit the star within a few years. No known comet family in our own solar system comes remotely close to this scale. The second hypothesis came from outside the team. In October 2015, astronomer Jason Wright at Penn State published a paper pointing out that the light curve of KIC 8462852 was consistent with what you might expect from an artificial megastructure, specifically a Dyson swarm. A Dyson swarm is a hypothetical collection of solar energy-collecting satellites orbiting a star, a concept first proposed by physicist Freeman Dyson in 1960. Wright did not claim this was the explanation. He explicitly noted it was unlikely, but he argued it was a scientifically valid hypothesis, falsifiable, and worth testing. The media had no such restraint. Within days, headlines around the world announced the possible discovery of an alien megastructure. This was not what the scientists said, but the story was out. A third line of inquiry was interstellar dust, material between us and the star rather than around it. If a cloud of interstellar dust happened to lie along our line of sight to KIC 8462852, it could produce dimming. But interstellar dust dims all wavelengths of light roughly equally, and later observations would show that this was not the case here. The century-long fade. Then things got stranger. In January 2016, astronomer Bradley Schaefer at Louisiana State University went digging through a remarkable archive. The Harvard College Observatory's collection of over 500,000 photographic glass plates of the sky, taken between 1890 and 1989. These plates, physical photographs on glass, represent a century of sky surveys, and they can be scanned and analyzed to extract brightness measurements of individual stars over very long timescales. Schaefer found that KIC 846285D2 appeared to have dimmed by roughly 16 to 20% over the course of 100 years. This was astonishing. F-type main sequence stars do not do this. They are stable. Millions of them have been monitored, and none show a century-long fade of this magnitude. If the finding was real, it eliminated almost every simple explanation, because whatever was happening had to operate on timescales of decades, not just days. The finding was contested. Other researchers pointed out that the photographic plates had been taken with different instruments over 100 years, and calibration issues could create an apparent dimming trend where none existed. A study by Michael Hipke and Kevon Stassen argued that the century-long fade was likely a data artifact. But then, a separate analysis by Benjamin Montet and Joshua Simon, using Kepler's own full-frame images from 2009 to 2013, found that KIC 846085-2 had dimmed by about 3% over those 4 years. The dimming was not steady. The star faded gradually for the first 3 years, then dropped more sharply by about 2% over just 200 days, then resumed its slow decline. Of a comparison sample of hundreds of similar stars, virtually none showed this behavior. So the star was fading, not just in dramatic day-long dips, but slowly, steadily, over years, possibly over a century. These appeared to be two manifestations of the same underlying process, and no one could explain what that process was. How the world got involved. What happened next was unusual not just for astronomy, but for how science itself can work. Tabitha Boyajian launched a Kickstarter campaign to fund continuous telescope time dedicated to KIC 8462852. The goal was to catch the next dimming event in real time, not with a single space telescope on a fixed schedule, but with a network of ground-based observatories that could respond immediately when the star began to fade. Over 1,700 people contributed. The campaign raised more than $100,000. Meanwhile, amateur astronomers from the American Association of Variable Star Observers began monitoring the star on their own, pointing backyard telescopes at a patch of Cygnus night after night. It was citizen science at both ends. Volunteers had found the anomaly, and now volunteers were helping fund and conduct the follow-up. The professional community was watching too. The SETI Institute pointed the Allen telescope array at the star, scanning for artificial radio signals across a wide range of frequencies. They found nothing. An optical SETI observatory in Panama searched for laser pulses. Nothing. Whatever was happening at KIC 8462852, it was not broadcasting. But the question remained, what was it? The dust answer. In 2017, something important happened. Boyajian and a team of over 200 researchers caught 4 new dimming events in real time using the Las Cumbres Observatory, the global telescope network funded by the Kickstarter campaign. This time, they had multi-wavelength data. They could observe the dips simultaneously in ultraviolet, visible, and infrared light. And what they found was decisive for at least one question. The dimming was not the same at all wavelengths. Blue light was blocked more than red light. Infrared barely changed. This meant that whatever was causing the dimming was not opaque. A solid object, a planet, a megastructure, a star, would block all wavelengths equally. Only fine dust, particles smaller than the wavelengths of light they interact with, would produce this pattern. Dust scatters blue light more effectively than red, the same principle that makes Earth's sunsets orange. The alien megastructure hypothesis was, at this point, effectively ruled out. Separately, a study by Huan Meng, using NASA's Spitzer and Swift space telescopes, confirmed the wavelength-dependent dimming for the long-term fade as well. The gradual dimming was also consistent with fine circumstellar dust, particles orbiting the star at some distance. Dust was the answer, or at least part of it. What dust does not explain. Here is where the story stands today. The long-term dimming, both the gradual year-to-year fade and the century-long trend, if real, is consistent with a cloud of fine dust in orbit around KIC 8462852, or possibly between us and the star, that is slowly evolving over time. But the short-term dips, the dramatic plunges of up to a fifth of the star's brightness observed by Kepler, are harder to explain with dust alone. To block that much light, even briefly, requires an enormous quantity of material. Dust fine enough to produce wavelength-dependent dimming would be quickly blown away by the star's radiation pressure. Something has to be replenishing it, or something much larger has to be involved. Several models have been proposed. One involves a large planet or brown dwarf on a highly eccentric orbit, surrounded by a massive ring system or trailing debris. Another suggests that the star recently consumed a planet and the resulting debris is still settling. A third posits ongoing collisions in a dense asteroid belt or a disintegrating body close to the star. None of these models fully account for all aspects of the light curve. Each explains some features while failing to match others. The irregular timing of the dips, their wildly varying depths and shapes, the combination of short-term events and long-term fading. No single mechanism has been shown to produce all of this simultaneously. As of the most recent analyses, the leading consensus is that circumstellar dust is the primary agent of dimming, but the source and dynamics of that dust remain unclear. What makes this star unusual? It is worth pausing to note what makes KIC 8462852 genuinely strange, because in a galaxy of billions of stars, strangeness by itself is not rare. There are variable stars. There are eclipsing binaries. There are young stars surrounded by disks of gas and dust that produce all manner of irregular light curves. These are all understood, at least in broad terms. KIC 8462852 is none of these. It is a mature main-sequence star showing behavior that has not been observed in any other star of its type. Other stars with large irregular dimmings are young, still forming, still clearing their birth material. KIC 8462852 is not young. It shows no signs of a debris disk in its infrared spectrum. Its spectrum is clean. It should be stable. There is one detail worth noting. In 2021, astronomers confirmed that KIC 8462852 has a companion, a red dwarf star, separated from it by roughly 880 astronomical units. For scale, that is about 30 times the distance from the Sun to Neptune. The two stars are gravitationally bound. Whether this companion plays any role in the dimming phenomenon is unknown. Red dwarfs at that distance do not typically influence the circumstellar environment of the primary star. But the fact that KIC 8462852 is not a solitary system adds another variable to an already complex picture. And there is the matter of scale. Kepler observed over 150,000 stars for 4 years. Among all of them, KIC 8462852 is unique. No other mature star in the entire dataset shows anything comparable. Whatever mechanism produces these events is either extraordinarily rare or requires a specific set of conditions that we have not yet identified. And yet, 22% dips, a possible century-long fade. Behavior seen in no comparable star among the hundreds of thousands monitored by Kepler and its successors. This is why the star still matters. Not because of aliens. That hypothesis was interesting, testable, and ultimately not supported by the data. But because KIC 8462852 appears to be doing something that current astrophysical models do not predict. When a mature star behaves in a way that no model explains, the models are incomplete. Something is missing from our understanding of stellar physics or circumstellar dynamics, or some process we have not yet identified. This is how science works. Not through answers that arrive neatly wrapped, but through objects that refuse to fit. The name. The star is formally designated KIC 8462852. Informally, it has two names. Boyajian's star, after Tabitha Boyajian, who led the first comprehensive study, and Tabby's star, a nickname derived from her first name, which stuck. There is also a third name, used in the original paper, WTF star. It stands for Where's the Flux, a reference to the missing starlight. The authors insist this was the intended meaning. Monitoring continues. Amateur astronomers around the world, coordinated through the American Association of Variable Star Observers, keep watch on KIC 8462852. Ground-based and space-based telescopes periodically revisit it. The James Webb Space Telescope, with its unprecedented infrared sensitivity, could in principle probe the star's environment in detail never before possible. Here is what is certain. There is a star, 1,470 light-years away, that dims when it should not. The dimming is caused by dust. The source of the dust is unknown. The mechanism that produces brightness drops of up to a fifth in a mature star remains unexplained. No other star of this type behaves this way. Here is what is not certain. Whether the century-long dimming trend is real or an artifact of historical data. Whether the short-term dips and the long-term fade share a common cause. Whether the red dwarf companion is involved. What specific physical process creates, sustains, and distributes the dust? What started as a citizen scientist spotting an oddity in a graph became one of the most watched stars in modern astronomy. More than 1,700 people crowd-funded telescope time. Dozens of professional papers have been published. The Allen Telescope Array listened for signals. NASA's Spitzer, Swift, and Kepler all contributed data. And after all of that, the star remains incompletely understood. That is not a failure. That is the normal state of science when confronting something genuinely new. The universe is under no obligation to be simple, and sometimes a single flickering light, 1,400 light-years away, is enough to remind us how much we still do not know. The data keeps arriving, the explanation does not, and the star keeps flickering. Don't forget subscribe, friends. We don't say goodbye.